Hello, everyone, and colleagues from Japan. Konnichiwa. My name is Omar. I'm a PhD student in University of Illinois, Chicago. And today I'll be presenting our project, Lightweight Temporal Consistency for Grid-Based Obstacle Detection in Edge Devices. As the title suggested, uh, we are going to focus first for the grid-based obstacle detection, the idea that we come up with, and the second is temporal consistency that we applied for grid-based obstacle detection. And unfortunately, I won't be able to there physically, but thank you so much, Dr. Arman Ruhi, today being there for us. Hello, doctor. And I hope you enjoy. I did my best to make this the presentation interesting and fun. Yeah, thank you. Yeah, basically there are two things that motivate us for this project. The first one is autonomy in robotic systems, and the second one is development on edge devices. As we all know, the obstacle detection is essential for safe autonomy, right? For example, navigation on robotic systems, systems like mobile robots, or it could be a Lego robot, or drones, because all these systems basically they need to move from one point to another point. And the second is development on edge devices, because eventually what we are trying to do is bring this autonomy into edge devices, means fixing those complex functions like navigation into a smaller boards. But these edge devices, they have speed constraint. For example, they are small in size. It might be advantages in many applications actually, but they have no CPUs. Since they don't have any CPUs, they are very lightweight. They have very lightweight computation, right? So, for example, if we want to display something on the screen, we have to use these old LCD displays. Since they are edge devices, we try to do computation in board. We don't want to communicate with the cloud or the master. So, because what we want, especially for these robotic systems to be standalone. So they do everything inside. They take some action, they process it, and they take another action, and maybe they can transmit the result. Yeah, and these edge devices are able to process the sensory data from very lightweight sensor. For example, a LiDAR sensor or depth cam, they cannot be processed using these edge devices. Uh, since we want these systems to be standalone, they have to use batteries because we cannot plug them into city electricity, right? So energy consumption is also another thing with these devices. Yeah, problem statement. So what we need is a reliable obstacle identification for safe navigation, right? But how we are going to identify these obstacles? There are different methods or different sensors that we can use. For example, lidars or depth camera, but those are, as we mentioned before, they require very high computation. So the cameras are still a good option because they are very lightweight in terms of their size or computation. And there are different versions like RGB cams or grayscale, right? The other problem is with the standard object detection models. So they are much more like general purpose object detections. So what we are looking is not basically an object detection. We are basically looking for obstacle detection, right? So they just identify the uh, the, the all the objects that they are on their data set, and they don't distinguish if this object is an obstacle or not. The other limitation with these standard models, they don't care about the distance awareness. For example, in this image, the first car, like it could be an obstacle, right? Because it is near, but the second, third, or the last one, they are far. Maybe it's not concerned yet. Maybe they will be in the future, but for now, they are not on example for an obstacle. Another problem is with resource demands, because the idea that we come up with, it should be applicable for different hardwares, right? Because some hardwares, maybe they are better in latency, they give less latency, but the other one might be give more might be more energy efficient, or the other one might be give more accuracy. So this idea should be fit in every different hardware. And lastly, real-time performance. So what we want from our system to be, it should be low latency. And of course, like there are some other models like cloud computing. In that case, we also have to consider the energy consumption for transmitting the data, or the latency while sending the data and receiving the result, maybe. So that is the basic idea of edge computing, right? So what we are trying to do actually is do the process inside the chip, inside the edge devices. So already in these robotic systems, what we are trying to do, create a standalone system, right? So that's why edge computing is a good idea for this type of applications. And after reviewing these problems, we come up with an approach to solve these limitations. So we are gonna see those approaches in for different fields. The first one will be the grid-based obstacle detection. That was the first idea that we come up with. So we introduced 8x6 binary obstacle matrix for compact spatial reasoning. So it gives us an idea where is the location of the obstacle. And the second is temporal smoothing, because there are some limitations. Maybe there are some noise while capturing the sample or image. So this is the stage that we overcome this problem in edge devices. And then we already discussed before. So this idea should be applicable for different hardware, right? So we have like hardware spectrum. Like we can apply this idea in different level of hardware, like microprocessor or a microcontroller, or system on chips like Raspberry Pis. And the lastly, since we are talking about obstacle, not object detection, so we need a different approach for our model and the data set. So, and last, we are going to talk about this. So grid-based obstacle detection. What is it? Basically, we convert object detection into a fixed 6x8 binary obstacle matrix. The image represents actually on the left side of the screen. So the object is detected, then we put binary values for each grids. So if the grid is 1, that means obstacle detected in that specific cell. If it is 0, that means there is no obstacle detected. It provides a compact and interpretable map, and its size is fixed. So it's kind of computational lightweight, because the size is fixed, right? So when we do computation, we don't need dynamic memory allocation. Or let's say if we get this obstacle matrix and we want to transmit it to the cloud, or to the master. So even the transmission is very short bandwidth, because of this small and fixed size. And of course, it works for all the models, different models. We will already talk what kind of models that we use. So it's applicable. And I also want to mention that, like, why we explicitly choose this dimension 6x8. Actually, we tried different sizes for this obstacle matrix. For example, for 3x4, but it was too coarse. Because like what we are trying to get from this obstacle map, where is the location of the obstacle, right? Like it could be on the left side of the image, or the right, or up, down. It depends again on the application. Let's say if we are trying to apply this idea on a mobile robot, so there is no going down or up. But if we are trying to apply this on a drone, so we can extend this, like drone can fly up and down. So a coarse matrix is incapable of giving this information. This is what we decide. And like if we increase the size of this obstacle matrix, so it is too complex. Basically, we need to compute a bigger matrix, right? But like there's a bigger overhead because and the output is same because what we are trying to do basically is like possibility of the direction. So we can get the same data actually from the 6 by 8. So we decide that the 6 by 8 obstacle matrix size is optimal for accuracy and efficiency. And how it works. So basically we capture an image. In this example, we use grayscale. Like most of the application, most probably we are planning to use grayscale because in edge devices we are mostly looking for uh, energy efficiency and accuracy. We can still get a good accuracy from this image, right? And we apply object detection algorithms to get what is the obstacle. So we create different data sets. We'll come up later about this. And these two steps might be in different hardware, or the model that we use for object detection might be different, but the output will be same whatever what. So this phase is just for the representation. Actually, what we do basically, these traditional uh, object detection algorithms, they give bounding box. So we just overlap, like if there's an overlap with the grid, so we just turn this grid to 1. It means the obstacle is detected. But the real output will be just like this one, an obstacle matrix. So it's still clear and give enough information to understand, like if we are going to use this for navigation. So it is obvious that like we should not go on the right side of the camera's objective, right? So we should go left. So and the second idea that we come up with, it was temporal smoothing mechanism. So why we need this? We need a temporal smoothing mechanism in video because raw frame by frame detection is often unstable or noisy. So what causes this type of instability or noisy? So it could be a blur motion if the object is moving so fast and the camera sensor is not able to catch that object in that frame. So it's going to be blurry, right? So it's again limitation for obstacle detection. Or lighting condition. Of course, actually we can overcome this problem using a better model, but since we are working with edge devices, those methods might not they don't fit inside this resource constraints device. And the last one is vibration. So for this vibration, actually there are some techniques on the software and hardware side. Like on the software side, we try to rid of this vibration, and on the hardware side, we use gimbals, right? So we try to tolerate this vibration, so we get better results. But still, we are working in the edge devices, energy constrained devices. So we have to come up with easier, lightweight solution. So how does it work in our case? For example, we capture an image. This is frame 1. And then let's focus for one specific cell. This is cell O 07 in that image in frame 1. And let's assume that we capture 5 frames. And the third one is a noise. It could be because of the vibration or like blurry image or any other reason. So we know that it's an noise, but like when we process it, we should know that like how we are going to identify it's a noise or not. So to overcome this problem, we apply a majority vote rule. So there are 5. We some of these values and divide it by a threshold. So we get the higher vote. And a cell is considered occupied only if it appears as an obstacle in more than half of the recent frames. So we just look for the recent frames. Again, there's a threshold or the size of the buffer that we are using. It is adjustable depend on the hardware that we are using or the application that we are using. And it's a nice example, actually. On the table, you see there are 15 frames. The second column, it is a row detection. Row detection. So as you see in first 11 frame, we should identify the object, but in frame 3 and 5 there's a noise somehow, but we should be aware of this. So when we apply this, so we are using a buffer. In this case, we for simplicity we use a buffer size of 5. Like in the beginning the buffer is empty, so it is just going to return what is the row detection. And when the buffer size increase, it is going to divide this with divide this buffer length with 2. Yeah, and of course, like there are some disadvantages of this, but it's negligible. What I mean with disadvantages, as you see here in the frame 12, like the object is missing, but we still like get in the smooth output, we still get uh, object is detected. So this smoothing is kind of give us the old data, but in many application this is negligible because this process happening in milliseconds. And in terms of efficiency of smooth motion, let's say for the navigation, the smoothness or consistent of changing in the data is more important. We explained the approach, but the thing we have to be we have to able to use this approach in different hardwares, right? Because different hardwares or different applications requires different hardwares because they have different priorities. So, for example, like if we are looking more on the accuracy, so then we can go with desktop or CPU based computers, or like mid-tier, then we can go with a system on chips. But if we are much more on the memory usage or power efficiency, then we can go with microcontrollers. So let's see them in details. So microcontroller level, for this we use FOMO. It is a model published by Edge Impulse. And if you are aware with this platform, so you might be aware the framework itself give and ready to use uh, program for Arduino or ESP. So once you create your model, you get the executable file. So we test our model using Arduino Nano. So the output is impressive because as you see the model size is only 70 kilobyte, and it uses only 123 kilobytes of RAM. And the latency, it includes three things: pre-processing, it captures image, and the other processing, grid-based obstacle detection, and the smoothing, combined of these three. And they're extremely, they require extremely low power. And the second level is system on chip. So it is mid-tier. So system on chip means it could be Raspberry Pis or NVIDIA Jetsons. So in this application, we use Raspberry Pi 2, 3, and 4. And to train the model, we use SSD mobile net. And the accuracy is moderate, and the latency is also moderate, and it is applicable for most of the industrial application like autonomous food delivery trucks. And yeah, for the power efficiency, we test this when we run these algorithms, temporal smoothing as well as the grid-based obstacle detection. Uh, it the power consumption ranges from 2 to 5 watt. And in some applications, we can still go with CPUs because maybe we don't have any limitation for power efficiency, but we have problem with the transmitting the data. So this level is still useful. So the model for this level is train it using YOLO, and the accuracy is the highest, and the latency is the lowest. Yeah. And the table gives the comprehensive comparison of these models with their model size, input size, pre-processing interface, grid, smoothing, and the total. So the image size is different in each hardware. The Arduino, for Arduino, we use 96 by 96 grayscale image. For Raspberry Pis, we use 320s. Again, grayscale, and for the desktop we use 642 480, again grayscales. Yeah. Another thing that we had to highlight, uh, it is model inference and the data set. So there is a vector robot, it is a companion robot. It's asking what's obstacle, right? It's a good question actually, because an obstacle can vary significantly depending on the application. So an object might be considered a target in one context, an obstacle in another, or entirely irrelevant in the third one. For example, if you are working with robotic arm for a pick and place application, the a box, for example, might be a target. But if a vector robot is trying to navigate through this box, it is not a target. It is basically an obstacle. But a box might be irrelevant for any other applications. And it's asking why we can't use the traditional models, right? It's actually it's very nice question. So let's go in details. So we are working in edge devices. Every bit of memory and the computation is matter for us. So we need to avoid unnecessary detection, which would waste our resources. Or traditional method like semantic segmentation can capture pixel level details, but it is computational, it's very heavy and it is not suitable for this type of edge devices. And the current data set, they are designed for obstacle detection, but they are designed for object detection, but an object might not be an obstacle. We give the example already. So we have to come up with some solution, right? To overcome these limitations, we collect only navigational relevant objects and train three different models for different hardware platforms. And as a result, as you see, so there are several columns on the picture, but we detect only the two nearest one, because the rest of them, they are far and they are not an obstacle for in the current position. And finally, experimental results. So on the left side of the screen, you see a row detection, and on the right side of the screen, you smooth grids. So if you look at it carefully, okay, maybe, yeah. Uh, if you look carefully, the object detection is inconsistent on the row detection. But if you look on the smooth version, you will see that it's more consistent. If the object is detected, it is still there, less noisy. And there is another thing. The results show that the obstacle which are near to camera's objective, they're detecting. Like if the object is far from the objective, we don't detect it. Uh, for example, here you can see the detection of the table. Like if the table is nearby, so it is detected. Or if the column is nearby, it is detected as an obstacle. For the future work, we plan to apply this grid-based obstacle detection to path generation for autonomous systems. Uh, So there's an example of this. So in the video, you see the best. Actually, it gives us a direction that we should that we can choose. So there's a probability distribution. Like there are different priorities. Like forward has the first priority because the camera is on the front side of the system. So if there is no obstacle we wanted to move, then left, right, up, and down. So by applying some smoothing methods for this result, for the best action, like forward and leftward, we are planning to get a trajectory planning algorithm. Thank you so much for being here today, and I hope you enjoy the presentation. So if you have any questions, you can reach out me the email that I put on the slide, or you can visit our lab website. Thank you so much, and arigato gozaimasu.